we talked about vertical asymptotes. Naturally, the question is, okay, what about horizontal asymptotes? So I'm going to talk about horizontal asymptotes now. I chose this problem, this function, just for kicks, right? Because it doesn't have any vertical asymptotes and it has a horizontal asymptote. And the graph is like this. It's not something that I will expect you now to be able to graph this, but in this class we'll learn how to graph this without a graphing calculator, but using calculus techniques to figure out what the shape of this graph is. But for the time being now, if you are faced with something like that, it's fine, just use a graphing calculator to get the picture. And as we see, on both ends for my long-time behavior of x, it looks like this thing is going to 2. And I know you guys did this back in pre-calc, right? Where they taught you the rule to look at the ratio of the top to the bottom of the largest power. We'll see that in not next week, I don't think, maybe next week, maybe week after, I don't know. We'll see that in a stricter sense. But for now, you can kind of use that or just use the picture. In terms of what that means from a point of view of the limit, what are we really doing with this? Well, rather than taking x to a particular finite point A, we're saying let's let x get very, very large, right? We're taking x to infinity. So that's what we mean by limits at infinity. In this case, I would write the limit as x goes to infinity. Oh, I guess I should have given it a name besides y of f of x is 2. Now, the limit at infinity, of course, is always a sided limit. You're always either going to positive infinity or to negative infinity when we're in the real line. Calc 3, that'll be a different story. But right here, we're on the real line. All we've got minus infinity or plus infinity. Yes, minus infinity or plus infinity. I was facing the wrong direction. Anyway, whatever. You get the gist. In this case, as is the case for most rational functions, the limit to positive infinity, the limit to negative infinity are both 2, right? Of course, that's not always necessary. If I take, for example, inverse tan of x, so inverse tan of x has 2 separate horizontal asymptotes, right? Because tangent has those 2 vertical asymptotes. We had this long discussion last week, right? This is my function. So in terms of how do I write this with the limit, I've been writing f of x here, but if the function is small enough, you could just put the function in there. Or if we have like a, something nice like that. And if I look at what's the long time behavior, as x goes off to infinity, I've got pi over 2 on the right-hand side, and I've got negative pi over 2 going out on the left-hand side. So as we know, a function can have one vertical asymptote, horizontal. One horizontal asymptote, 2 horizontal asymptotes, or no horizontal asymptotes. That's all the options you have. Okay, so what happens if a function has no horizontal asymptotes? Well, we can still talk about the limit as you go out to infinity. So let me pick a nice function that we know very well. How about y equals x cubed? Since I always use x squared, today I'm mixing it up and using x cubed. So obviously there's no horizontal asymptote. This limit doesn't exist. The right-hand limit doesn't exist. The left-hand, like the limit at infinity doesn't exist. The limit at negative infinity doesn't exist. But this is the same kind of thing in this case we can be more specific about the way it doesn't exist. So if I look at what happens with my function x cubed and think about what's happening over here where x is getting very large and positive, x cubed is getting very large and positive. So I would say that this limit doesn't exist, but I can be more specific and say that it grows without bound, it goes to infinity. And on the left-hand side, it goes without bound and negative, so it goes to negative infinity. Okay? So, and we can write down sort of an intuitive definition for the limit for all these cases like we did. I don't know that necessarily have to do that, right? Let's see what else I can say about this. Okay, so there's a couple of different things we can do. Let's talk about some other behaviors at infinity that we might see. If I look at sine of x, we know what this does, right? So if I look at this, not only is there no, it's not going towards any line, it's bouncing between -1 and 1. There's nothing I can say about this. Like, there's no way it's not going to infinity, it's not going to a number. For this, I can just say that the limit does not exist. So I would just write does not exist. And if I was asked why it doesn't exist, I would say that it oscillates between -1 and 1. Or you can say that it's oscillatory. Okay. Now, it's not just the fact that it's oscillating, but the fact that it's oscillating and it's never going anywhere. It's never going down. Because you can have an oscillation and it can still be going down to something. For example, let's switch it up a little bit. Let's do y equals sine x over x. We talked about this when we were interested in what was going on at 0. So I had put it up on Desmos before Desmos started to hate me. And we zoomed in to what was going on at 0. But if you remember, before what was going on at 0, you saw more of the graph. And if you go and look at it now, it does this. And it's the same on either side, but I'm pretend my thing is actually nice and symmetric. This one looks good. That one looks wonky. But anyway, it does the same thing on both sides. And what you'll see here is that, yes, it oscillates, but the amplitude is decreasing. And you can see that because if I write this, this is like 1 over x times sine x. So as x goes out to infinity, this is kind of like a changing amplitude, and that's going to get super, super small. So it's going to squash down that sine x that we had in the previous picture. And so just from this picture, I can see that the limit as x goes to infinity of this function sine x over x is actually 0. And the same thing, of course, is going to happen on the other side. And you're like, wait, it's sine x. But remember, it's sine x times x, so it is odd function times odd function. You do get an even function, so that makes sense. Both sides are going to be doing the same thing. They're both getting squashed down to 0. Oops, I forgot to put the negative here. Sorry, guys. Negative infinity. All right, so we have that. And just sort of visually from the graph, so just because it's bouncing back and forth doesn't necessarily mean it doesn't exist. But if it's bouncing back and forth and not getting really small, then it's going to basically not exist. In fact, we can have bouncing back and forth and getting really big too. We'll just keep using sine x, right? So, for example, if I want something that does that, let's say I did, say, x sine x. If I graph x sine x, actually, I can cheat a little bit so it looks better. This is the value of y equals x. So that's like going to be what the thing is on there, the amplitude. This actually is going to look like this. And sort of the same thing, again, it's going to be the same thing on the other side. I'll kind of try to make it look like the same. Again, because it's going to be x. Pretend it's the same on either side, right? It's supposed to be. Again, it's going to be an even function because it's odd times odd. But in any case, here you have a situation where it's definitely going to 0 at 0, but as I go off to infinity, it's growing. Not only is it bouncing back and forth, but it's basically bouncing back and forth between positive and negative infinity. So the best I can say is does not exist in this case. All right. Okay. I think I covered all the possibilities. And this is just sort of more of a heuristic thing so that we can kind of talk about the behavior at infinity. Later on, next week, we're going to talk about how to find the limits algebraically, both limits at a point and also limits at infinity. And then we'll get more into that more correctly then. But just to sort of have an idea and to have pictures in your mind of what these different limits might do and what possible behaviors exist.